Welcome, everyone, and thank you for joining us this afternoon. I'm Andrea, and I will be your host for today's session. I'm glad to welcome today Suresh, who is the Executive Director at Secure Systems Research Center in TII, Technology Innovation Institute. His research focuses on zero trust security for SOCs, and he leads a team to build an open source SOC, advancing security research and IP development. In today's presentation, Suresh will present his work applying zero trust principles to building a secure RISC-V system. Suresh, now I would like to invite you to start your presentation. Thank you.
My pleasure. So thank you for the opportunity. And my name is Suresh, and I work in TII, it's Technology Innovation Institute in Abu Dhabi. So today we are going to talk about applying zero trust principles and building a secure RISC-V system. And what we hope to learn from today in 30 to 40 minutes is this one. So what cyber physical system, why security is important for them, and zero trust. We talk a bit about the drone systems, RISC-V, which is a free and open instruction set architecture, and a RISC-V based platform. And at the end, as Secure Systems Research Center, what we do and how we can collaborate. So a quick introduction, if you're not aware of the cyber physical systems, which are unmanned and autonomous. CPS are basically cyber and physical. So they are computer systems that interact with the physical world, where laws of physics govern their behavior, and they have to support real-time guaranteed performance in a safety critical manner. It integrates sensors, processors, actuators. If you see the picture here, it represents both the cyber and physical aspects of the thing. So it has both sensors to read the environment and then take action using actuators. Quick examples are a self-driving car and drones, as you are already aware. And as these systems get more complex every day, every month, with adding more sensors, more data gets generated, the establishing confidence that they work perfectly and correctly is becoming challenging. So that's something we will explore, how we can fix that problem. The typical attack surface would be around all these things, right? So things like actuators missing their deadlines. So some action has to happen and it doesn't happen. Another thing could be on the communication side. Somebody can do a man-in-the-middle attack, and then they could block your resources by jamming or whatever, and they can easily cause a denial of service to the sensors by maybe blinding the camera, or it can be anything. So on the computing side, likewise, they can introduce some timing error or some fault injection, whatever it is. So I think this gives you an overview of the attack surface. And if anything is compromised, it's going to be catastrophic. So it has to be very carefully implemented to be safe and secure. And even if there is an attack, it has to be contained locally. That's the premise of CPS. And you know, you must have read in the newspapers, a machine learning algorithm in a car actually sees a person's photo in a bus, and then it thinks there is a person, and then it stops. So these are vulnerabilities in today's systems, and then we need to address all of them. And people can attack your car through a smartphone and then make it do whatever it wants. And something related to drone is whenever the drones fly across these power transmission lines, due to high EMI, electromagnetic interference, the GPS accuracy goes for a toss, and then causing the IMU to go berserk, and then the drone crashing. So these are some things we need to address. We will see some of them today. And by trust, there are many aspects to it. So I won't trust let's say, a device if it is not secure, if it's not safe, if it's not reliable. So trust is a basically overloaded term here. There are a whole bunch of things like two sides of a coin, right? So each of these things have to be addressed for me to trust a device or trust some machine, trust my car. So that's sort of the scope of the trust. For today's discussion, we're going to focus on autonomous edge, which is at the intersection of IoT, machine learning, and cloud. And that happens to have the drones and autonomous cars, autonomous boats or whatever. It's a big, big market, worth around $100 billion. So we will focus on this piece, but whatever we talk is equally applicable for anything you see on the left or right. So for this, for the focus today, it's going to be edge. And we pick drone as a example platform for here. So some of the use cases, we know, right? Drones act as a first respondent. For example, when there's a fire, the firemen use the drone to actually go inspect and then come back with a report, and they plan what to do next. It can act as a delivery drone. It can do video surveillance and a whole lot of things. So they are pretty useful stuff. This slide gives you a brief overview of a system architecture, at least how we are building in TII. So we have two types. Basically, one is fog and the other one is edge. One has more capabilities because it talks to the cloud. It does a few other things like mission planning and a whole lot of things. But there are two processors here. One is flight controller and mission computer. So we will talk about them shortly. And what you see here on the edge drones, they are like in swarms. So they'll be like 10s or 15s talking to the fog drone and then carry out their mission. This is a quick overview of how the software architecture will look like. So we use the containerization. That means using VMs with isolated partitions here for each activity. For applications, there is a container here. And for flight critical operations, there's a container. For security, you see a dedicated VM. So the idea will be, even if there's an attack, let's say some attack happens from the network, and then let's say you make the networking VM crash, it's not going to impact your rest of the system. So you can borrow some time and then you can try to reboot this VM only. That way guarantees a whole lot of reliability and resilience to this architecture. So if you notice here, these two flight controller and mission computer are the two chips that I talked about a minute ago, and both of them will have a root of trust. So that's essential for establishing trust. Okay, so what are the existing threats and mitigations in this sort of system? On the left-hand side, you see the common threats that we find, right from hardware attacks, cryptographic attacks, supply chain attacks. So if you look at the 10 items here, I have classified them into these buckets here. So let's take a few examples, right? So single point of failure. So what if you have one sensor and somebody introduces some sort of fault? What will happen? Will your system crash? So for that, we use redundancy. So let's say GPS. So what you do is you put 2 or 3 GPS. Just to be sure that even if one goes out of whatever goes into a toss, you still have the other 2 to gain back control. And the popular things that we find in other categories of devices like phone or laptop, the secure boot, the secure storage, having a root of trust, all are already taken care here. It's been these been pioneered for many years already, And the drones that you see that you can commercially buy, all of them have such mitigations already addressed. So my question is, what's next, right? So that's an interesting question, and I have zero trust to come for rescue. So zero trust, before we actually go into how we do zero trust for the RISC-V system, let me give you an overview of what the term generally is. Forrester back in 2010 had coined this term for networking basically, and it is built around the concept of never trust, always verify. You see here on the left-hand side, this is, let's say this is a corporate setup, and then they trust what is inside, and any threats from outside are filtered with firewalls. So what happens if there is a local attack, and it cannot mitigate that? So that was the weakness of that model. So the networking side switched to so-called the zero trust model, where there is no implicit trust zone. And each of these boxes that you see are the smaller trust zones, so which are protected by themselves. And it verifies each and every transaction that comes from outside. So what it essentially means is a smaller blast radius. Even if there is a one bad guy, he cannot screw up the whole system. So this model assumes breach, assumes vulnerability already exists. And if something is compromised, then try to fail safely and securely. So this model is also applied recently in 5G and 6G core architecture as well. So with that in mind, let's dig a little bit deep. There are 10 pillars for zero trust. Verify explicitly, least privilege, and these are pretty known things if you had worked in security for a long time. But never mind, we will see a few things here. So verify explicitly, it means it verify every access without any trust assumptions, right? For example, a data packet coming from somebody, you don't know from where it comes, but you verify and authenticate before consuming that packet. Similarly, you have least privilege and assume breach that we talked about in a minute ago, and then fail securely. So if there is an error condition, don't just crash or fail. You make sure you do it properly without leaving any secrets around or anything like that that compromises the security. And something on 8 is secure the weak link. So we know the weakest link in the chain is the problem. So we need to address the weakest chain first, and simplicity to end with. So you can take a look at this one when you have more time. So we're going to jump straight in on the context of RISC-V system. This is a onion diagram. If you peel onion, you see layers. So that's how I see the system, basically. On the top, you have applications, and then you go down to system software, then you have platforms, then you have the SOCs. So whatever the items you see, they belong to the particular ring. And if you see the IP here, your processor, your machine learning, everything is sitting here. So what we're going to do, layer by layer, we will see how to apply these zero trust principles and go from there. Okay, so I have sort of categorized into 4 things here. So the platform will have PCB, an SoC, one or more SoCs, and a bunch of peripherals and software. So what you see on the right are some zero trust capabilities that are in the research, or that something we are already working on. That's going to add value to the trust, security, resilience, all these parameters we looked at. So let's start by looking at the platform level. Platform level, the first threat we are going to look at is component authenticity. So what this means is, how do you know a component that is plugged into your board, for example, GPS, is authentic? Is it genuine, or is it being tampered with? Does it have the right firmware image? How do you know? You simply trust because it's already sitting on the platform. So there are two categories here: active components and passive. Active means there could be a microcontroller inside with a root of trust. For example, would be a coprocessor or a flight controller. Passive components such as sensors or actuators, which are pretty simple, and they don't have this intelligence inside. For example, a motor controller for the drone, they are pretty much passive, and then there is no root of trust or whatever it is. So how do we make sure this is addressed by a proper means? You don't have to trust, but you establish the trust. So this is with a process called mutual authentication. So on the left-hand side, you see for active components, there are few standards called SPDM and PCI-6 integrity and data encryption that actually talks about mechanisms to establish this trust by having the platform root of trust talk to the active component root of trust, and then exchanging certain certificates, and then verifying the measurements, and then exchanging some keys to make sure the data transfers are all encrypted and authenticated. We could use this in the drones or whatever context which is already there. But the main issue is, what about passive components? Say you want to authenticate an LED to make sure the LED blinks when you send a command. Is the LED from a credible source, or is it tampered with? We never know. So how do you do that? So we need to do some research and understanding or exploring some ideas to make this happen for such constrained devices. For example, power constrained, resource constrained. Things may not even have a crypto engine or crypto capability inside. So one example we could see is QRNG, which is a quantum random number generator, which is a photonic chip, by the way. So as we know, it's a passive component. And then how can we verify the authenticity? So there are certain ways in which you can check certain quantum traits of the output that it generates. So by observing those patterns, we can be sure whether on the other side there is a genuine photonic chip or not. This is an example. Similarly, we need to do some research as a community and then come up with alternative approaches for other passive components. That way, so the zero trust principle we use here is verify explicitly. So verify before trusting anybody. Let's look into the next thread, which is sensor spoofing. So what you see on the left here, somebody is using a laser pointer to take down a drone. So basically you are saturating the camera and then some outputs from the camera, making some machine learning model crash. So this is the integrity and availability of the sensors basically by introducing fault. And the impact will be the reliability and stability of the platform. So as you know, some RF signals are being used for in the sensors, right? So let's say a camera sensor looks at light to make an output here. So when you tamper it, when you corrupt it with some extra light, it's gonna go berserk. So this is a way of tampering the sensors, no matter what, how much secure the other things on the upper layer are. So the only solution we know at this point of time is using redundancy. So popular redundancy mechanisms that are available are homogeneous and heterogeneous. A simplest example could be, let's say you have GPS, you put 2 more GPS, and then you have 3 GPS. So, and you aggregate the outputs from each of them, and then you consume them. So even if one fails, you still have the other 2 running. This is not very practical for a drone use case, because are you going to overload the drone by tripling every piece of component you have? What happens to the power, size, and battery capacity? So that's not really ideal for these kind of devices. Let's look at heterogeneous. For example, in the self-driving cars now, what if the camera is spoofed? Then what it does is it uses the LiDAR and applies either sensor fusion before giving to the machine learning, or use a parallel pipeline and then do a comparison before taking an action. So there have been some attacks where people tamper the signboards. So let's say it's 30 miles per hour, and you tamper the signboard, and they make it 200 miles an hour, and this car can misinterpret and then get into trouble. So for that purpose, they have used this sort of heterogeneous redundancy. For GPS, for example, the GPS goes for a toss. We can use the barometer or altimeter outputs to make sure is everything fine, or something is being attacked or something like that. So this is a popular way that we use now. Can we do something better? So basically now there are some optimizations we can do here. Instead of triple module redundancy, we can optimize one, and having 2 modules with a new capability called checkpoints. So you basically take snapshots and check checkpoints as you execute. When there is a problem, you can always roll back or roll forward to regain the stability. So what really happens is you got rid of one, so it directly saves power, and but you pay for checkpointing penalty. Look at on the right side, it's even better. So what really happens is you got rid of the second, also not 100% though. We keep that on standby, and whenever you want to run, whenever there is a fault on module 1, module 2 is always ready to run from the previous checkpoint. This is very valuable to perform minimal risk maneuvers. Things like, let's say, let's take an example on the car. Let's say the brake failed, or some CPU failed. What can you do? The best thing would be to bring your system to the safe state, such that no accidents can happen. So it will try to bring the car, maybe try to stop in a safe place. So for that to happen, you need the module 2 to come up and then do some minimal stuff. So these are ongoing research here, and then we are trying to see which one is more suitable for these kind of applications. Of course, it looks simpler than how we can implement basically, and I think yeah, we will see some progress soon. Next category is at the SoC and CPU level. You will see the next threat as fault injection. Basically, you introduce a fault into the system, either naturally or unnaturally, and make the system deviate from its expected behavior. I just put a figure here just to illustrate, right? So let's say the drone is extremely hot, flying in Abu Dhabi's summertime, and from the packaging material, there's an alpha particle, and then that hits the SRAM cell. Yeah, there is no ECC because these are IoTs and small devices. ECC is error correcting code mechanism that comes up with its cost. The area, power, all shoots up by approximately 30%. So some of these low cost devices don't have that. And what happens is some data or something got flipped. Let's say the sign positive 40 became negative 40, and that caused the program to crash and then perform a wrong maneuver. So that's still very bad. So what is the recommended option for that? On the left side, you see, without anything, let's say today, if there is a fault and the logic CPU or anything it is, right? Anything, it could be microcontroller or a machine learning engine, whatever it is, it does a incorrect behavior. On the right side, this is something we are proposing and working on, by basically augmenting the logic with a monitor or a rule checker, which is a machine learning model that basically checks the behavior of this piece of logic and also sees what action it is taking. So, and if that action is wrong, and then it checks its rules basically, and then see if there is a violation, it takes over, brings the system to a safe, secure, and reliable state. So this is formally verifiable because we may not be able to formally verify and test the heck of out of all these logic. This could be really big, right? Let's say Linux, it's a million lines of code, and then it's really hard. So this one is much smaller and simpler compared to what you see on the left side, basically the logic. So this is really relatively easy, and these have rules. You can have rules for security, safety, reliability, anything you name it. And then these are human readable, auditable, and learnable rules. So let's say we step into a situation which was not known earlier, and the rule checker stepped in and it did some action to bring the machine to the safe state. And now it knows, okay, there was this condition, and then I better learn. So this next time, I'll be more safe and more secure than before. And it also uses, the next page, I will show you some things here. Basically, humans are also in the loop. So it doesn't just learn or whatever by itself. It does with consulting the experts. So, okay, so this one, let me elaborate a little bit more. So the rules, as I mentioned before, safety rules or security rules, we can begin with some initial set of rules. And let's say the security expert or safety expert writes certain rules, and rules are learned, and you have the monitor here. So what really happens is when the target logic, let's say, behaves badly, any rule is violated, and then it puts the logic into quarantine. It could be maybe, let's say, something went wrong, and simply restarting that logic or something like that could potentially solve the problem. But it puts in quarantine, and then it makes sure the system goes to safe or secure or reliable state that causes no harm or hazard for anybody. And after that, it learns that piece of thing, so that next time you don't have to basically always put the system into safe or secure state. There could be other ways to handle that situation. So that's about this one. If you have any questions, we can address at the end. The next threat is supply chain attacks. So both hardware and software can be attacked. For example, let me show you here on the bottom. This is about hardware. So let's say a design company makes the design for the chip, and it outsources manufacturing and testing and fabrication. Let's assume that is uncontrolled. Maybe it's in a different country, and then geopolitical things can come in, and then let's say you don't trust. So what really happens is potentially IP theft or counterfeiting or overproduction, or anything can happen where your IP or your trade secret, whatever it is lost. We don't want that to happen. So in this thing, we will look at the first one basically, which is related to hardware. And software things are not in scope for today, because these are basically encryption and basically attestation and stuff. So we will look at logic locking, which is a basically old technique, but it is really getting matured now. Basically key-based locking, just like you do it for a software, or let's say you have a password to log into your computer. Similarly, there are keys that can be attached to the system. If the key is invalid, the system won't function as expected, and only with that key that function works. So from the left-hand side, you see the design goes through, and in the middle, you lock that piece of hardware, and that key stays with you, right? For example, in this case, a 128-bit key that stays with you. You outsource the design to a foundry, and as long as it's outside, the chip is locked. So it's not going to function. Even if you try to modify or try to inject some logic or try to reverse engineer or copy, it's going to be dead. It's not going to be for useful for anything that anybody wants. So then after the manufacture, the chip comes back to you, you insert that particular key and the chip works. That's the idea of logic locking, basically. And the principle we use is difference in depth. Okay, so next one, control flow hijack. So on ARM and x86 platforms, we already have such mechanisms, but not on the RISC-V side. So basically things like buffer overrun can actually smash the stack using return-oriented programming. And you could also do tampering of the code to perform a call or a jump to an invalid function using several techniques. You can figure it out from the picture from below, right? So I mentioned two attacks here. So one is a stack corruption. So this was the original stack, and then somebody tried to do a buffer overflow or code injection, and this stack is gone. So what happens when you try to return call a ret instruction? It just goes to a bad code. Another scenario is you wanted to jump to a function called test, but you try to attack some of the registers or some memory content. So that made the flow to jump to somewhere else. So basically, you bypass this critical piece of code. So these two things, let's see how we could mitigate. So the currently proposed mitigation for CFI are one is using a shadow stack. So whenever the master stack is modified, the shadow stack is also modified. Whenever there's a mismatch, you know something got corrupted, and then software can take corrective actions. Second one is what is being proposed is to use landing sites where there'll be a register. So you load some unique signature before doing a jump, and after the jump, the first instruction will check this value here, right? So compiler inserts these labels basically, and then if they don't match, it causes an exception. So this way, even if you have to compile the code, it will protect such sort of attacks. This already is proposed, and it's already available in other architectures. Let's see what something new we can talk about here. So this one talks about using machine learning. Of course, the previous ones are needed. You need the shadow stack, you need the landing sites and stuff, but can we do something better to address future challenges in the control flow integrity, like control flow bending or whatever? What if there are no straightforward ways to fix them? So this talks about using machine learning to look at the flow of instructions, basically looking at the fetch unit and the decode unit, and then trying to learn or trying to infer from what you learned any specific patterns that will deviate or hijack your control flow, and then taking corrective actions. You can raise an exception, or you can you can maybe abort the program or whatever. So this research is ongoing, and then I just wanted to quickly share this before we go to software level. Software level, we have two things to share here. First one is attack on the data in use. For example, today, the code or data at rest is all encrypted. And then that is on the communication channel is also encrypted. But what if somebody attacks on the device while it is being used? So that's something on the other platforms we call confidential computing, where it could be encrypted, or there are hard isolation barriers to make sure nobody can get to the data or whatever it is. So there are malwares or something you can install and then trying to get somebody else's data. This is most dominant on cloud systems where there'll be multi-tenancy. So on the same server, you will have code and data running from, let's say, 2 banks. And then what if the other bank wants to snoop into the other bank's data? But on our use case, let's say from a edge or a drone sort of system, so far the multi-tenancy has not become a major use case. So, but things like keeping the data private and not tampered is something that'll be very useful. For example, a drone camera that is surveilling, it doesn't want the data to be leaked. So the interesting one will be just a data enclave, and application and VM enclaves are at this point of time for this particular device is not relevant, but for clouds and laptops and phones, it may be. So we will take a look at the confidential computing a bit. A gentle introduction, what we are trying to do on the RISC-V Foundation, basically to build a partition here. On the left-hand side, what you see is non-confidential VMs or applications or even operating systems. On the right side, using hardware techniques like memory isolation, integrity and replay protection, root of trust, IOMMUs, and whole lot of hardware support. We are building on top in the M-mode firmware a mechanism to isolate the untrusted side with the trusted side. The gray boxes that you see are what you call confidential VMs. So you can have your data here, which is isolated from the rest of the world, and then you can even have it encrypted. So you can protect the confidentiality and integrity of this the secret that you have. As of now, the idea is to just use existing instruction set and just use APIs and interfaces to the M-mode firmware. And then eventually, if there are any ISA needed, we will try to extend. So this is a defense in depth game. So now you see how we actually map the zero trust principle to each of these features that we talk about. The last one is about the code and data that's not on the CPU side. So let me give an introduction. The trend in the past decade has been more and more demand for compute. With the CPU core is not able to really cater. So we've been going in the heterogeneous special hardware path. That's how we got GPUs. That's how we got AI accelerators. So what really happens is the TEE, if you know, trusted execution environment, they are designed particularly for the CPU. So the code and data that is confined to the CPU is only being protected. Anything other than that, let's say GPU, or let's say peripheral. You have a peripheral that is attached to the PCIe, and then what happens to the code and data? It's left open now. Pretty much the TCBs since fixed at the design time, it cannot be modified at a later point. So these are some issues that prevent protecting the non-CPU or peripheral code and data. So with weak isolation, you're going to have problems with it, both in confidentiality, integrity, and availability. So let's see the before and after here. So before, you could have the TE enclaves here. So these code and data are running on the CPU. So these are isolated. These are protected already. But what about these GPUs and AI accelerators and the LTE peripheral that's attached? On the right side, what we think and what we propose is to have enclaves extend to these devices as well. So their memory, whatever the code and data running on the GPU or machine learning, they are also now protected. So that will ensure a platform level trusted execution environment. This has been prototyped on a Keystone platform, and then we hope to extend this even further for RISC-V. So that sort of concludes the brief, gentle introduction to the problem, the kind of solutions we are thinking about. So we will talk about the future directions here. So we know cyber physical systems need end-to-end security, resilience, and trust. Zero trust principles that we've seen proliferate across the supply chain. And specifically for the drone, the UTM or the UAS traffic management. So just like your airplanes, the traffic management also extends to the drone class of devices. They are now evolving. So security has a big role to play there. And I would like to give a call to action. I think as a community, as researchers, we need to accelerate this by bringing some standardization to zero trust architecture. We don't want different communities to develop divergent solutions. There is one thing that's happening in the RISC-V communities. We are developing a platform security architecture specification. So anybody who makes RISC-V platforms can refer to that and then stay consistent and then more secure. And as a community, if we can build open source reference platforms that addresses some of these challenges and compliant with the zero trust and so forth, it'll be fantastic. And last but not the least is contribute to RISC-V's security groups. You can join, for example, the trusted computing group that talks about many of the things we discussed. And then you can directly contribute to the specifications and stuff. So with that, I conclude my talk and then open up for questions. If we can address now, it'll be fantastic. Otherwise, you can always contact me.
Thank you very much for the presentation. We do have some questions lined up in the chat box. I think I can read them out loud to you. And if you want, you can also check them in the chat box. The first question is, what is the metric to calculate the severity of the threat?
Okay. So if you, let me take you to one of the slides before. So, okay. So you see here, what you do is Google search for this term, CVSS V3 rating, and then there you get a questionnaire in a web page where you think what you think is your parameters, like let's say I stands for integrity. So for this particular threat, integrity is most important, and then that value is high. Similarly, you put for all other questions it asks. C is for confidentiality, A is for availability. So you fill up the questionnaire and then it will bring you a score. That's going to be the severity score. Let me know if you need any help offline. I hope that answered. Okay.
Next question is, in RISC-V, the proposed CFI feature attacks are in software level. Does it require any privilege escalation at hardware level?
Okay. Okay, these proposed mechanisms are in hardware and software and compiler level, basically. So there'll be certain hardware changes like implementing a shadow stack. And that doesn't need, that's software transparent. Whenever there's a mismatch, you will get an exception. But the other one, like I mentioned, there is an ISA specifically for the landing site. So instruction change, compiler has to recompile your code and then insert certain tags onto the runtime code. And that's the how it's going to work. But the piece about privilege escalation and hardware level, it's not quite clear. Maybe you can talk to me and we can have a chat afterwards.
Thank you for answering this question. The third question is, what is your opinion on the many logic locking techniques and the attacks proposed so far? Most of the proposed mechanisms are broken, but they are broken using only simple benchmarks like the ISAS ones. How can those attacks scale with bigger designs?
Yes, we know logic locking has gone through at least 1 or 2 decades of reinvention. Once something is attacked, somebody comes up with a new mechanism. But I believe it has matured enough that in our current SOC that we are building, we are adding logic locking actually, and then we are pretty confident that it doesn't suffer from some of the things you mentioned here. But we can definitely talk about it, and then you can help to break it, and then we'll fix it together, right? So feel free to send me the paper that you mentioned about ISCA, and then we can talk about it.
Thank you very much. And one last question that I saw, do you have any document white paper for RISC-V scenarios discussed?
Okay, document white paper, of course, yes. What you do is, for example, just send me an email, and then I can send you some of the specifications that the community is now working on. For example, the control flow integrity architecture specification and confidential computing specification. So you can come and take a look, and then bring your suggestions and bring your contributions to make it even better. Some things we have not thought through, or some community members are not thought through, and then you have some insights. You're welcome to give that suggestion, and then it's a collaborative effort. So I hope to get an email from you, and then we'll take it from there.
All right. Thank you very much for the presentation and for answering these questions. I don't see any other questions, so I think we can conclude the presentation. And in the meanwhile, I would encourage you also to check out the training offer for the upcoming hardwear.io USA conference and trainings. I hope you have a nice day ahead, and see you next time. Thank you again.